All right, kids, here's the first lesson of the next unit. It's about circles, which seem cute and soft and cuddly and round and something you already know about. But let me tell you, there's a lot going on with circles. There's a lot of terms today. There's a lot of things you thought you might know or maybe forgot about. Or anyway, keep your antennas up. This is maybe going to surprise you on some stuff that you thought you knew about. First of all, what is a circle in the first place? A circle is the set of all points that is a certain distance away from a designated center. The center is very important. Usually that's actually how we name the circle. So if this was point A or something, ooh, that's a really big clunky marker. That's all right. We would call this circle A, and that's the notation you'll see in the book. Make that thinner. That has everything to do with the circle. The circle is defined as all points that are a certain distance. Oh, this is called the radius. My thinner pencil. They're all this far away from A. This is all the points that are that far away. And that's pretty easily defined, but if you think about it, there's a little bit more to it, actually. It's kind of complex. All right, so here's some terms associated with circle that you may or may not have heard before. A chord, and I put a little picture in here. This is not in your notes. You might want to draw this. The chord is this little segment right here. The endpoints are on a circle. We didn't really, maybe I didn't make this clear enough before, but the circle is just this green stuff. This stuff in the middle here, this is technically not the circle. We could say it's part of the interior of the circle, and this is part of the exterior of the circle. The circle itself is just that green stuff. All right, so the segment has points on the circle. That's called a chord. And yeah, this point's called part of the chord because it's part of the segment, so that's okay. Anyway, this whole thing is called the chord. The diameter is this whole entire segment here. You don't have to designate the center, but I was trying to show it here that it was going through the center. You probably knew that one. Congruent circles. Circles are congruent as long as they have the same radius. So I drew two circles here with the same radius and said up here, well, yeah, they're congruent. That forces circle A to be congruent to circle B. And any other circle I drew that had a radius congruent to CD will be congruent to these. Concentric circles, first of all, they have to be coplanar. Usually not a huge concern, but yeah, technically they have to be on the same plane. And they have to have the same center. So they kind of look like circles of a target or circles of ripples, that kind of thing. You could have lots of other circles that have the same center. And the centers, of course, don't have to be equal. All right, more terms. Terms. And if you want to rewind and go back and look at these again, not a bad idea. I left the center on these for no particular reason other than to show you that the center doesn't necessarily have to have anything to do with it, with certain things. Kind of like on this one, this chord here does not go through the center. It usually doesn't. If it does, it's called diameter. This thing, this inscribed quadrilateral I've drawn here, has nothing to do with the center. So you don't have to show that. I just showed it here so you know that it doesn't have to have anything to do with the chords of that quadrilateral. So this is a quadrilateral, but you could have more sides. As long as all the points are on the circle or all the sides of the polygon are chords, we would say that is inscribed. Circumference, I tried to highlight it here and make it dark. It's the circle itself, but when we use the word circumference, we're talking about the length of that. So the length of this green thing is the distance around the circle. We call that the circumference. And for the first time ever this year, we're starting to use this symbol. This is called pi. We'll talk more about this in class, but I'm sure you've heard about it before. It's the ratio of the circumference to the diameter of a circle. No matter what, it says down here, no matter what the circumference of this circle is, if you compare it to the diameter of that same circle, it's going to take this many of them, and you should remember this. It takes a little more than 3 of them, of those diameters. If you had those, whoops, I wrote that in the wrong order. If you had this 10 centimeter segment, or whatever these units are, in rope or something, and you try to lay them around this circle, it's going to take about 3 and a little more of one of them, so a little more than 3 of them to go perfectly around the circle. No matter how big the circle is, it will always take that many diameters to reach around the circle, and it's so important it gets its own symbol here. So you can find the circumference by taking pi times the diameter, or if you just knew radius, you could take 2 times the radius and get the same thing as if you were working with diameter. So you can think of circumference as 2 pi r or pi d. So up here, I would say the circumference is 10 pi. And just like when we're working with square roots, we could take the answer 10 pi as the exact answer, or we could put that in the calculator and we'd get something like 3.1415. I'm multiplying that by 10. I would usually want 2 digits, so I guess that would be a 2, wouldn't it? Rounding that up. Okay, guess what? More terms! Central angle. Okay, central angle is this thing. It's a good name for that. It's an angle at the center. So angles YOE. Oh, he said YOX up here. Let me change to YOX. That's a central angle. The one that he mentions here is YOX. That's this one. Okay, I'll play along. Fine. An arc is a portion of the circle defined by two endpoints. Okay, you know what I'm going to do? I'm going to put a little squiggly line under this. Oh, my squiggles aren't big enough. Okay, squiggly line under arc, because then I'm going to do a squiggle in this arc. So here's an arc. He marks here as arc YX, and there's a little eyebrow kind of mark up here. This is not the segment marking. This is an arc marking. It's supposed to look curvy, like a little contact lens someone put up there. So minor arc YX. See if I can do this on my little pad here. So here's that squiggly line. This is arc YX. So that's why I did that squiggle there. Arc YX is this portion of the circle, and it has a length and it has all kinds of properties, but this technically is the arc. The arc is this figure. And when we use the letters YX and just two letters with the arc thing on top of it, we're talking about this trip from Y to X, not this trip from Y to X. So notice how it said shortest. An English teacher might make you say shorter, because there's two. Anyway, when you're going from Y to X along the circle, there should be a short way and a long way. Most of the time, there's arcs of different lengths. When they just use two letters, they mean the short one. If they use three letters, they mean the long way. So YEX is the rest of this stuff that's still green and I haven't marked on yet. If you want to talk about this arc, YEX, it's all this out here. The measure of a minor arc is the measure of its central angle. So this angle in here, we found out, I don't know, it looks like it might be 100 degrees or something like that. We could say if this is 100 degrees, then we would say the measure of arc YX is also 100 degrees. So measures of arcs are made in degrees. By the end of this lesson, we're going to talk also about the length of arcs. And this is kind of hard to keep straight, but we've got measures of arcs and we've got length of arcs. Measures of arcs are how many degrees they go around their circle. Length has to do with, like actually inches and centimeters or that kind of thing. So an arc, it's hard not to say mark. Measure of arc is mark, no. Measure of arc is in degrees, length of arc is in length. And every arc has both those things. It has a degree of curl, basically, and it also has a length. All right, use three letters again for major arcs, but you also use three letters if you're talking about a semicircle. EX here is a diameter. So if I said arc EX, it would be kind of ambiguous, like do you mean this arc or do you mean this arc? So for a 180, you have to use three letters. So we'd either say EZX for this one, or if we were talking about the one on top, we'd say EYX. Total measure of a circle is 360, you probably knew that. Measure of a semicircle, which is what we call those like EZX, where it's a diameter at the ends of it, that's 180. And the major arc and the minor arc have to add up to 360. So if I took the measure of, another way to say that is this, the measure of arc YX plus the measure of the major arc from Y to X, so like YEX. I don't know what they are, maybe, but I do know that when I add those up, I'm always going to get 360. Okay. Adjacent arcs of a circle are arcs that have the exact line endpoint in common. That's exactly like adjacent segments. It's a little bit more kind of string along here because if you're talking about one arc and then the next arc, they would have to be along the same circle, and they don't really have to be collinear in a line. Anyway, adjacent arcs, I could say YX. Oh, let's just do it here. I have arc YX is adjacent to, I could say, well, XZ is adjacent to it. How about that? XZ, because they meet at X, and they don't overlap. So they have exactly one point in common, and here that point is X. YX is also adjacent to arc EY, or even I could say it's adjacent to arc ZY. Congruent arcs are arcs in the same circle or in congruent circles that have equal measures. Okay, so because of that whole length business could be different even if the arcs have the same measure, then we have to qualify this by saying they have to be in congruent circles. But if we're sure they're in congruent circles or the same circle, because the circle is congruent to itself, if as long as arcs have the same measure, then they're going to be congruent. That's easier to see than to talk about, actually. I'm not even going to talk about that here because it's not really a problem. In the above diagram, chord ZX cuts off two arcs. Look at chord ZX. Oh, let's do it with this. talk about chord ZX cuts the circle into two arcs. There's the arc on this side. Oh, let's make different colors now. The yellow thing cuts us into, there's a kind of a green arc on one side, and then there's kind of a blue arc on this side. ZX is this green one, so I'll highlight that with the blue, and the green one was ZX. The arc of chord ZX is the minor arc ZX. So since this chord, you can kind of say, well, it's associated with the green arc and it's associated with the blue arc. So which arc is kind of the arc of that chord? The one we kind of favor in all these, just like when we did two letters and there's nothing else to tell you otherwise, we always favor the minor arc. We're always going to favor the minor arc here. So ZX, you think about the arc that goes with it kind of the most. Think of the minor one, not the major one. The minor one's more interesting. It's the one that's going to have a measure less than 180. And we usually, as you probably know already, we care more about things that have a measure of less than 180. How often have you heard us talk about, oh yeah, this arc has a measure of 210 degrees? Like, that's just not done. We don't talk about 210 degrees. We'd rather talk about the 150 degrees on that side. So minor wins any ties, if you think about it. Okay, so here's those theorems from the book, but it's the same. Oh, sorry, no, this is a little different. In the same circle or congruent circles, two minor arcs are congruent if they have the same central angle, so if they have the same measure. So if angle 1 is congruent to angle 2, yeah, this is from the notes a second ago. If angle 1 is congruent to angle 2, then this thing is congruent to this thing. And it could be that it had a different circle that was congruent to this circle, had the same radius, and had another angle in it that was congruent to 1 or 2, then its arc would be congruent to those also. Arc addition is just like segment addition. If we talk about the measure of arc zy, and of course that's in degrees, added to the measure of arc yx, its degrees, the angle altogether in degrees would equal this arc of zx. So you can add arcs together and they add just like segments or angles. That's not supposed to be surprising. We'll do some of these problems and you'll see how that works. The sector of a circle is the region bounded by two radii and an arc of the circle. I'm liking my highlighter today. Oh, let's use a new color we haven't used though. This will be fun. All right, so the sector, yay, purple. The sector is, whoa, it's all this stuff in here. So the sector, I lost my shading. Oh, now I'm shading over my shading and it's looking, I had little teeth in there. I didn't mean that. It's like Pac-Man with teeth. Oh, that's so cool. I did not mean to do that, but it's like Pac-Man with fangs. That's so awesome. Anyway, all the purple stuff is the stuff inside the sector AOB. It's bounded by two radii and the arc of the circle. So it's like the stuff inside Pac-Man's mouth. There's also, which might accidentally look like fangs, which is cool. But anyway, all the purple is that. There's also a sector out here. So I could talk about a major sector too. Since the sector is a portion of a circle, we can find its arc length by finding we can find its arc length. So we can find this, I should get rid of the purple because now you can't see what I had in there. You could find the length of that by finding the ratio that this angle is, notice these are the same. This is x degrees because it's the central angle. The arc out here measures the same. Yeah, this is going to take 2 videos, I can tell. We got a ways to go. Anyway, this area can be found, or this length can be found as a proportion of the entire circle. I know that, I mean, right now this looks like it's about 90 degrees. If this is 90 degrees, then this length here is going to be 1/4 of that full circumference. And I don't think that's hard to imagine. If x were 90, let's just say if x were 90, then I don't think it would be hard to figure out that what we have here essentially is 1/4 of the circle in that area. Well, I think you could estimate that in your head, but really what you're doing in your head is you realize, or your head realized anyway, that 90 out of 360 happens to be 1/4. And we're always going to use this kind of trick. If I knew that that angle x, say it wasn't 90, say it was like 88 88 degrees, then I know I have 88 3/60ths of a circle in this portion. And we'll use that trick, so x out of 360 times the circumference, to find the length, whenever we need to find the length of this little arc right here. So this little arc, if this is really 90, this little arc is 1/4 of the full circumference. All right, I'll pick it up there in video 2. Hopefully I'll get done in video 2. See ya.